In this last video, we'll talk about how to determine whether two events are independent or not. So this says we have a hypothetical distribution of gender and major of students in an Intro to Stats course, and then whether the student was a social science major or a non-social science major, and whether that student identified as female or male. And it's kind of an interesting distribution, one that's very strange. We wouldn't probably see this in real life, but we have this very kind of symmetric distribution. And I want to determine whether the events the student is a social science major and the student is male, if those events are independent or not. Now, oftentimes if we are just working with events that are kind of relatively easy to understand and wrap our head around, things like flipping a coin or rolling a die, we can usually intuit whether or not those are going to be independent. But I think it's a lot more difficult, particularly when we're working with a two-way table. So in order to determine if two events are independent, we need to look at the probability of A given B, whether that's equal to the probability of A. Now, it doesn't really matter which event we label as A or B. What this is saying is that the given B right here, the probability of A given B, knowing that B has happened or B is true, doesn't affect the probability of A at all. That doesn't change anything. So if these two probabilities are equal, then they are independent. If they are not equal, then they are not independent. So let's go ahead and have the student be a social science major. Let's have that be our event A, and the student is a male as our event B. So probability of social science major given that they are a male, is that equal to, and I'm going to put a little question mark over that, is that equal to the probability that I select a social science major? So let's start with the conditional probability on the left first. I know that I am choosing from the male group. So from the male group, that means I'm only looking at this row right here. That's the only one that matters to me. I have a total of 50 males in my sample. So out of the 50 males that I have, we had, let's see, 30 of them are social science majors. So 30 out of 50. If we wanted to go ahead and divide that out real quick just to get a fraction, we get a nice even 0.6. So that is 0.6. I want to know, is that equal to just considering all social science majors? So if I go back and look at my table, and now I'm just going to consider the probability that I select a social science major, knowing nothing else about this. So if I'm just selecting a social science major, well, that means I'm selecting out of the 100 individuals in my survey. So out of the 100 individuals in my survey or in my class, how many of them are social science majors? Well, we had a total of 60 social science majors. So 60 out of 100, I can divide that out. 60 divided by 100, well, that's going to be another 0.6. So yes, these are in fact equal. We don't need that question mark there. 0.6 is in fact equal to 0.6. That means that these two events are independent. Now, it worked out nicely here because we had this like very symmetric and honestly very interesting distribution that we had here. I would wager to guess that most of the time if we have just any old arbitrary contingency table, you're not going to see this symmetry and you're probably not going to have independent events, but we did in this hypothetical scenario.